The following is a video lab report demonstrating Newton's second law shown by the movement of a ping pong ball by Morgan Jackson, Physics 2211, Dr. Greco, Section MO2. Here we can see the raw video footage taken of the ping pong ball rolling across the ping pong table. The ball was pushed just to the left of the frame and rolled across the screen. This was done so that while the ball was in the center of the screen, it would be moving at a constant velocity rather than at the initial start time where it was accelerating from rest. There is a standard ruler placed in the center of the screen to measure the length of the ball and also to give a reference point for the viewer. Before we do anything else, first we have to identify the system and the surroundings. The system in this experiment contains the object whose force we are studying. Here that would be the ping pong ball. The surroundings are everything else acting on the object. This would include the ping pong table, force exerted on the ball by the table, as well as the atmosphere. It is also important to identify the goals of this experiment before discussing methods and analysis. The goals in this experiment were to analyze the movement of an object moving at a constant speed by tracking the position of the object as opposed to time, to verify that the velocity is constant by constructing a position versus time graph, and to make a model representing the movement of the object. The big overarching concept of this lab was to show how a ball moving at a constant velocity can be shown with Newton's second law. If we look at the equation, final velocity equals initial velocity plus net force over mass multiplied by time, we can see the relationship of these variables. If we substitute 0 for F net, we get an equivalent final and initial velocity, meaning that the change in velocity over the interval would also be 0. Here we can see additional calculations surrounding Newton's second law. The observed start time was 0 seconds, and the time of last observation was 0.767 seconds. The diameter of the ball was 0.0378 meters, and the mass of the ping pong ball was 0.0025 kilograms. Using the first two data points from the data calculated from Tracker, I was able to calculate the initial velocity as well as the initial position of the ball shown here. I also included the calculation showing the relationship of average velocity being distance over time for further clarification. Using Tracker, I was able to track the position of the ball as time progressed. As you can see, the ball was placed on the x-axis and traveled in the positive x direction. After marking each individual position in Tracker, data was provided to quantitatively show the relationship between time and position. Next, using VPython software, I was able to use the data calculated for initial positions and velocities, as well as time intervals and ball dynamics to write a code for a representative model of the ping pong ball. Here is a picture of the model as well as the graph constructed from the model data. Accurate comparisons can be made between the ball and the model by constructing position versus time graph in Google Sheets. Here we can see very similar graphs, however they do not line up directly. Potential sources of error will be discussed later in the video. As we examine the contents of this graph, it is important to not only discuss implications of the data, but also analyze meaning behind the numbers. In this position versus time graph, we can see that Newton's second law was proven by the slope of the line shown. As we anticipated, the line is positive, sloping upward. This shows that the ball was heading in the positive x direction, which it was, and also at a constant velocity without speeding up or slowing down. As we are analyzing this experiment as a whole, I believe it's important to discuss the merits as well as flaws of this experimental design. The ping pong ball was a fairly good representation of a model for a constant velocity. However, by rolling the ball by hand, it was difficult to record the ball with a consistent, steady velocity. The ping pong ball table used was a fairly flat surface and was good for video. However, the table had a slight slant on it, causing the ball to roll slightly downward as it slid across the table. This experiment, however, did show consistent data with the model constructed. But using a ball of slightly larger weight might have helped keep the direction and position steady. Now I will discuss some theoretical questions regarding the experimental design. The first one being, what if the axes were flipped? If the axes were flipped in this model, all that would change would be the slope. If I rolled the ball backwards, it would be in the negative x direction, and the graph of the position versus time would be negative sloping, starting at the origin. All other data would be the same, just the direction vector would change. The next question to address is, because we say that net force is equal to 0, what forces are acting on the ball to make it that way? The initial acceleration of me pushing the ball overcomes the air resistance to a point where those forces don't matter individually. The total force is 0. When the ball is in that period of constant velocity for a period of time, the forces all cancel each other out.